converse of Lagrange's theorem is need not be true. Okay, proof of this converse of Lagrange's theorem. How to proving this theorem? Their converse is true or not. Okay, so converse of Lagrange's theorem. Converse of Lagrange's theorem need not be true. Converse of Lagrange's theorem need not be true. But before statement of Lagrange's theorem, what is statement of Lagrange's theorem? If H is subgroup of G and G is finite, means G contains finite number of elements, then order of H divides order of G. That is, this statement is if suppose that order of G is equal to n. Okay, if order of G is equal to n, then and H is subgroup of G, then order of H, whatever order of H is whatever may be, but their order is which divides n. Okay, their converse is converse of Lagrange's theorem. Converse of Lagrange's theorem. What is converse of Lagrange's theorem? Their converse will be if here order of H divides order of n, then H is G has a subgroup of order n. That is, if D divides n or D divides order of G, then means any divisor of order G, then D divides order of G, then G has a subgroup of order D. Means if G has any number divides order of G, which has any number divides, then G contains a subgroup of order D. Okay, so there which is this statement is need not be true. Okay, so therefore counter example is G is equal to, suppose that A4 group, alternating group which contains all U1 permutations. Okay, A4 group, order of G is, this is alternating group with 4 symbol, alternating group with 4 symbols. Okay, so their order of G is equal to 12. Okay, because order of n is equal to n factorial upon 2. Okay, using this order of G is equal to 12. Okay, but A4 has here 6 divides 12. Okay, divisor 6 divides 12, but A4 has no any subgroup of order 6. 6 divides 12, but A4 has no any subgroup of order 6. Means A4 has no subgroup of order 6, means any subgroup of A4 which has a no order 6. Okay, how to prove this theorem? Suppose that if possible, suppose that A4 has order, A4 has a subgroup, their order is 6. Okay, if possible, suppose on contrary to showing this, if possible suppose H is subgroup of A4, H is subgroup of A4 of order, suppose that any subgroup of A4 which has a order 6. Okay, and then to show that on contrary to possible, suppose A4 contains a subgroup which has a order 6. Okay, therefore order of A4 is uh, 12. Okay, order of A4 is 12 and order of H is equal to 6, and therefore factor group or index set IGH is equal to index set, their order is order of G divides order of H, means index is 2. This is written in the form of also G over H. Okay, here index of this given set, index of H is equal to factor group index is equal to 2. Therefore, by using theorem, if any subgroup any factor group of index 2, okay, means any subgroup of H, any subgroup of G which has a index 2, then given subgroup H is a normal subgroup. Okay, using this here index 2, which implies that H is a normal subgroup of G. G is A4, that is H is normal subgroup of A4. Factor A4 means index 2 means in factor group G over H contains only 2 cosets. Okay, index means their index 2 means which contains only 2 cosets, and 2 cosets which is are H and any other elements. H is itself and one is sigma H, suppose that. Okay, the question group, the question group A4 over H, G over H has only 2 elements, means factor group contains only 2 elements, and their elements is a left and right coset. Okay, 2 elements H and any other element, suppose sigma H, where sigma does not belongs to H and sigma belongs to A4 elements. Okay, sigma belongs to A4, sigma is any permutation. Okay, therefore H and sigma H are elements of A4H, means factor group. Okay, that is factor group A4 over H. Factor group A4 over H has order only 2, has order 2. Okay, so this is 2 elements H and sigma H is belongs to factor group this. Okay, therefore since in any group of order 2, any group of order 2 contains any group of order 2 contains a element square of each element. Any group of order 2 elements contain square of each element. Square of every element is equal to identity. Okay, square of every element is identity. Okay, since that is G is a element contain only 2 elements, then A square is equal to identity must be only if G contains only 2 elements, then any group contains only 2 elements, then every element of square is equal to identity must be. Okay, so every element contains identity, therefore A4 over H contains element, or in A4 over H, in factor group A4 H, square of every element, square of each element in square of each element in A4 over H is identity. That's it. A4 over H contains 2 elements, that is, and factor group identity is H itself, that is identity is H. Okay, that is therefore A4 over H is equal to A4 over H is contains only 2 elements, H and sigma H. Okay, and each element square of each element is equal to identity H itself. Okay, so here H square is equal to H into H, and their value is also H. Similarly, and sigma H Similarly, sigma h square is equal to sigma h into sigma h is equal to sigma square h, and their value is also h. Okay, because square of every element is equal to identity of factor group is h itself. A over h is equal to h itself. Okay, so using this all, square of each element is equal to h, identity means h itself, but square of every element, square of every element in A4, square of every element in A4 is, suppose that choosing any one element, suppose that choosing any one element, suppose that 1 2 3. Okay, 1 2 3, then which can be written in the 1 2 3 means this is permutation. 1 has order 2, 2 has 3, 3 has 1. Okay, which is equal to, then there this is cycle in cyclic from 1 to 3, if which is written in the form of 1 2 and 1 3. Okay, if squaring of this element means 1 2 3 2 3 1, their square is equal to multiplication of this 1 2 3 2 3 1 into 1 2 3 2 3 1. Okay, so their value is 1 2 3 3, 1 has 2, 2 has 3, 2 has 3, 3 has 1 and 2. Their value is, if we written in the cyclic form, their value is 1 3 2. Okay, this is written in 1 2 and 1 3. Okay, this is written in the form of 1 3 1 3 and 1 2. Okay, therefore here 1 3 2 1 3 and 1 2. Okay, then next this is also belongs to in H, because their square is means square of every element in A4 is also in H, Okay, and so we observe that here consider any one element from this element is suppose that this element is belongs to in H, then there this element is choosing from A4. Okay, this element is choosing from A4, then this is belongs to in A4, suppose that, then their square is also belongs to in H, because here square of each element is also belongs to in H. So 1 3 2. Okay, 1 3 2 is also belongs to in H, then their square again 1 3 2, then their square 1 3 2 means this permutation 1 has value 3, 2 has value 1, 3 has value 2. Okay, then there's is again 1 2 3 1 2 3 in cyclic form we return, then there 1 2 1 3 1 2 1 3, which implies that 1 2 square into 1 3 square, and this is if squaring of again is this element. Okay, their value is again 1 2 3, this is also belongs to in H, suppose that. Okay, this is also belongs to in H. In similar way here, their value, this is one element, suppose, then 1 2 4. Okay, consider this element 1 2 4, choose another elements. Okay, choose another elements 1 2 4 from A4, then their square is square of this element is 1 2 4 into 1 2 4 in cyclic form. Square means 1 2 1 4, which can be written in transposition form. Okay, 1 2 1 4, their value is 1 2 square into 1 4 square, means 1 has value 2, 2 has value 1, 1 has value 4, 4 has value 1. Okay, then their multiplication is uh, 1 has value 4, 4 has value is 1 has value 4, 4 has value 1, 1 has value 2, means 1 here 1, then 4, then 2. Okay, their value is, if, and this is belongs to in, this is also belongs to in H, because square of this element. Okay, again this one element, this second element, then consider 432 their square 432 means 432, 4 has value 3, 3 has value 2, and 2 has value is 4. Okay, using this multiply this 432, 3 2 4, then their multiplication is 432, 4 has value 3, 3 has value 2, 3 has value 2, 2 has value 2, 4 3. Okay, this is 4 3 sorry 4 2 3, 4 2 3, this is also belongs to in EH. Okay, this one element. Next element is suppose that 314 square is equal to 3 ones 4 square is equal to 314, 3 has value 1, 1 has value 4, 4 has value 3 into 314 then their multiplication is 314, then 1 has value 4, 4 has value 4 3 1. Okay, this is 341, 4 has value 1, 1 has value 3. Okay, this is also belongs to in EH. Okay, then next element is suppose that 324. Okay, this is choosing from sigma square A4, then their multiplication 324, there 243 into 324, their value is 243, then their multiplication is 324, their multiplication is 3 has value 2, 2 has value 4, 3 sorry 2 has value 4, 4 has value 3, then 2. And this is also belongs to in EH. In this way, here this one element, this is second, third, fourth, fifth, sixth, and again two elements is suppose 143, their square is suppose 143 is 143, 1 has value is 4, 4 has 3 1, then there is multiplication 143, 431, their value is 143, 1 has value 4, 4 has value 3 1 4. Okay, 4 has value 3, 3 has value 1. Okay, and this also belongs to in EH. Therefore this shows that H must have at least 8 elements, which are therefore by using in this way, if any square of elements of in A4 is also in EH. Why? Because EH contains only 6 elements, but here in this way continuing EH contains at least 8 elements. Okay, then in this way this shows that EH contains 8 elements, because this 6 element and EH and sigma H, this 7 and this 8 elements. Okay, so therefore this shows that EH must have at least 8 elements. Okay, and which is contradiction to order of H. which is contradiction to order of H is equal to 6, and therefore H contains 8 elements and order of H is equal to 6, which implies that our assumption was wrong. Therefore our assumption is wrong. That is order of H is not equal to 6. Okay, that is order of H is equal to not 6, and therefore A4 has no any subgroup of order 6. Okay, so this is proof of our converse of Lagrange theorem. So how to proving this theorem? Here converse of Lagrange theorem is, if any element divides order of G, then G contains a subgroup of order D. Okay, for this here counter example is G is equal to A4 alternating group, and alternating group A4 is order of 12. Okay, but 6 divides 12, 6 is divisor of 12, therefore A4 contains a group of order 6. This is not possible because A4 has no any subgroup which has order 6. Okay, so if how to proving this A4 has no order 6? If you are considering if possible, suppose H is subgroup of A4 and their order is equal to 6. Okay, their order is equal to 6 means if order of H is equal to 6, then their factor group over H, A4 over H, their order is 2, means A4 over H contains only 2 quotient, index 2, which implies that index means number of left or right quotients. Okay, so using this index 2, which implies that H is normal subgroup of G, means G for A4 over H, A4 over H contains only 2 elements. One is identity must be belongs to in this identities must be belongs to in a factor group, and second is sigma H. Okay, suppose sigma this element sigma is not belongs to in H, and this sigma belongs to A4. If sigma belongs to H, then sigma H is equal to H itself. So therefore H and sigma H are distinct element. Okay, here where sigma H is not equal to sigma H, these two elements are distinct elements, therefore H order of A4 over H is equal to 2. Okay, so here any group containing two elements, means order 2 square of in every element is equal to identity must be, because result is seen that in previous lecture, if G is equal to only contains 1, suppose minus 1, then square of every element is equal to identity, minus 1 square is equal to 1 identity. Similar way, in this way here H contains 2 elements, which imply that square of every element in H is equal to identity. Okay, is equal to identity in A4 over H, but identity of A4 over H is equal to H itself. So identity over H itself, therefore here H square is equal to one element choosing H square. Okay, then their squaring H, is equal to H into H is equal to H itself, but sigma H square is equal to sigma H into sigma H. Okay, this is left quotient, this is left quotient, their value is sigma into sigma H. Okay, using this AH into BH is equal to ABH, using this result their value is sigma square H, but square of every element is equal to identity, which implies that sigma square H is equal to H itself. Okay, therefore square of every element in A4 is in H. Okay, that is square of every element. This means that sigma square is a element, sigma is a element of A4, then sigma square H is equal to H is also belongs to in A4 over H, which implies that when this element is belongs to in A4 over H, if sigma belongs to H, then sigma h is equal to value is h, and here sigma square h is equal to h, which implies that sigma square which belongs to in h. In this way square of every element here but not right, but which implies that sigma square is belongs to h. Here choosing number of elements in A4, suppose square of every element in A4 is also in h, because sigma belongs to A4, then sigma square h is equal to h, which implies that sigma square belongs to h. Using this result, therefore choosing this element, continuing in this way, choosing one elements from A4, 1 2 3, this permutation, one permutation, then their multiplication, square of this multiplication, this also belongs to in A4, this one element, then their squaring 1 3 2, 1 2 3, 2 3 1, this is choosing one elements from A4, then their square is also belongs to in h, this one element is belongs to in h. Okay, then second element choosing from A4, okay, 1 3 2, then their square element is 1 2 3, 1 2 3 is also belongs to in h, because sigma square belongs to in h. In this way here each element, square of every element in A4 is also belongs to in h, and therefore this one element, this is h1, this one element is belongs to h, sigma square h, this is second element is also belongs to in h, this is third element, this is fourth element, 6th, 7th and 8th. Okay, in this way h contains 8 elements. Okay, these all elements are belongs to in h, and h is subgroup of G, which implies that h contains 8 elements, and which are all are different element. Okay, these elements are all are different element, therefore h has order is 8, but our assumption is h has order 6. Okay, A4 has order 6, and therefore which is contradiction to order of h. Okay, therefore our assumption was wrong, means order of h is 6, which is not possible. Okay, which is not possible, therefore A4 has no any subgroup of order 6. Okay, this is a converse of Lagrange's theorem.